audience. We'll just wait for the door to close for a second. Great. So, moving on to our first speaker, we're excited to have Wahaaj, who's completed his PhD under the Marie Curie Bioimplant ITN program at IHDI Materials in Spain, developing a bioabsorbable magnesium PLA polymer. You're making it difficult for me to read today. But this polymer composites for orthopedic applications. And during his PhD, he was awarded the Innovative Process of the Year by the International Magnesium Society, which is really interesting, for developing a continuous coating process for thin magnesium wires at Neotech GmbH, Germany. At the moment, he's working as a postdoc in the ERC project MULT2D with Professor Ted Wogan to investigate the impact of type 2 diabetes on bone fragility. So without further ado, we'll go with Wahaaj's presentation. Take it away, Wahaaj. Thank you.
Thank you for the nice introduction. It's the first time I heard such introduction. So, okay, my name is Wahaaj, and I'm going to present the multi-scale effects of type 2 diabetes bones. The work I'm going to present today was supervised by Professor Alicia McNamara and Professor Syed under the ERC project, as she mentioned. So, yeah. So, a brief introduction about the diabetes. So, diabetes affects around 10% of the world's population. It's one of the most prevalent disease. And out of those, about 25% of those have type 2 diabetes. So, just before moving forward, I want to talk more about type 2 diabetes. So, in this type of diabetes, beta cells gradually decline, reduces to I would say, it stops to produce insulin. While in the type 1 diabetes, they completely they don't produce any insulin. So it is also linked with obesity, like most people have these kinds of diabetes. When the statistical studies were performed, it was found that the patients with type 2 diabetes have around 3 times more risk of fractures. But paradoxically, the bone mineral density, which is the indicator of fracture risk, remains unaffected. That's the major problem in this type of diabetes. So most of the studies have suggested that type 2 diabetes weakens the bones in multiple ways, like affecting the structure, composition, and cellular behavior. Another major challenge in this category is that, which was often overlooked in the past 10 to 20 years, that people mostly focused on studying the effect on long bones, like of tibia or femur. But recently, in the past 4 to 5 years, people started correlating the vertebral fractures. And when they correlated, they found out that if someone has type 2 diabetes and vertebral fractures, then they are more likely to have other kinds of fractures. And this is also linked with mortality. So it's an important bone to study in type 2 diabetes scenario. And we have very poor understanding of this bone. So the seminar I'm going to present today has a goal to understand the multi-scale fragility mechanisms in type 2 diabetes, particularly in the vertebral bones. And I would like to share this how these mechanisms changes with age, particularly the growth of the bones, how the structure of the cortical and trabecular bone changes with age, mineral density, how the vascular canals and lacuna inside the bone, they changes with the diabetes and with the age, and how all these mechanisms are linked with the decline in mechanical properties. And I would also share how these properties are changing, if there are any vertebrae specific effect, and also is there any effect of the region of the bone. So our group carried out the animal study. And in this study, we had male Zucker diabetic fatty rats. This is a very standard model for study diabetes. And we have 2 kinds of strains, control and the diabetic. So diabetic rats are fed with high fatty diet, so they develop obesity with time. And their beta cells functions is disrupted. They stops producing insulin. So diabetic rats feel more hunger, they eat more and develop obesity with time. And we have two age groups, 12 and 46 weeks old. So 12 weeks represents the pre-diabetic stage. They are just starting to develop the diabetes, while 46 weeks old rats represent the established diabetes. And we are studying these four bones. And I showed graphically like we have the stack of the vertebrae, and we are just focusing on these four L3, L4, L5, L6 vertebrae. And there are multiple tests, but the main focus is on X-ray based imaging. So another purpose of this seminar is to highlight the power of this new technique we have in the university now. And another major characterization technique was the image processing. And finally, we performed some compression test. So before moving forward, I just want to share a small video of what bone we are talking about. So I hope this video works. Okay, so this is how the vertebral bones looks. So in each of those bones, we are going to look at the vertebral body. So not all the processes, just this section of the bone. This is more prone to fractures, and we are going to see the dens and the trabecular, which is spongy bone, inside separately, and how this bone is affected by diabetes. So you can see the complex nature of the bone. So for those who are not into the bone, this could be like interesting to know before moving forward. So in terms of growth, we measure number of dimensions of the bones. These are how the scans look after the X-ray imaging. So the images are very close to what you get in the SAM image. So it's very nice you can get those stacks in 3D volume. So I want to just show the two major dimensions, which I think could answer my main question, whether diabetes affect the growth of bones or not. So first is the height of the vertebral body. And initially, both diabetic and the control rats is similar heights, but there's a lot of data. But if we just focus on just one vertebra, we could see that the growth of the bones is a bit compromised. So the diabetic bones are a bit shorter in the end of at the end of 46 weeks of age. Similar trend was observed in the width of the body. So we have a similar trend with the age. The width is slightly short. So this is how it looks schematically if you see on the right. So initially, both red, the diabetic, and the blue had a similar structure. But with the passage of time, the controls are a little bit taller than the diabetic ones. So the main takeaway is that the diabetes affects the growth of the bone. Secondly, I want to talk about the bone morphometric properties, which are used to characterize the structure of the bone. And there are a number of things we can study. And this is how the bone looks in terms of the cortical and trabecular bone. So the blue one is the cortical thick bone, and the black is the spongy bone inside the vertebra. So I will just want to present here the main two properties, which is the cortical fascian area. So what happens with the denser bone with the aging and with the diabetes. So initially, both diabetic and the control rats had more or less the same cortical area, like same denser bone volume. But with the time, we found out that the cortical bone is compromised a lot and is a lot more thinner than the control bones with the aging. And similarly, we see that trend with the trabecular spongy bone volume. So initially, the diabetic rats had a bit more trabecular bone, but with the time, we found out if you see the dark red and dark blue, so the diabetic bones has compromised architecture and compromised volume of the trabecular bone as well. So overall, the main takeaway is that the denser bone is affected most, and while the trabecular bone is also affected moderately with diabetes. And you can see graphically here, the yellow arrow shows the cortical bone. So on the left, you have the healthy old rat. So the shell is a bit thicker, but with the diabetes, you have a very thin bone around this vertebral body. The next thing I want to talk about is the bone mineral density. So mineral density represents somehow the strength of the bone, and it is usually used to assess the fracture risk. And in these scans, we can calibrate the pixel intensity with the mineral density. So we use these scans also to study the mineral density distribution. So a lot of data, but the main takeaway is that if you see both the cortical and the trabecular mean mineral density, we found out that there's no change in the mineral density with age or with strain. So you don't see any significant markers here. So that's the paradox. That's the main problem with the type 2 diabetes. In osteoporosis and other diseases, the mean density shifts, but in type 2 diabetes, although the cortical and trabecular bone is affected, but you don't see any change in the mean mineral density, which makes it difficult to assess the fracture risk. But if you zoom in and if you plot how the distribution of those density is, so we found out that in type 2 diabetes, in both cortical and trabecular bones, the heterogeneity of the mineral is increased. So there is kind of an old bone which is present, which is not being replaced, and the new bone which is being formed is getting mineralized in a slow manner. So the way the mineral gets mineralized and replaced is affected in type 2 diabetes without changing the mean of this mineral density. The last mechanism is about the vascular canal and lacunae analysis. And this is the main novelty of this work. So before moving forward, I just want to show the small video. Here it works. So on the top, we took the same bone, we took the scan at a very high resolution, and you see the cortical bone section here. So on the right, you have the vascular canals. These are very small intracortical canals which carry the blood vessels. And the blue ones are lacunae, which carry the osteocyte cells. So we study these both osteocyte, lacunae, and the vascular canals to see how these structures changes within the cortical bone with age and with the strain. So and on the top you see how the volume of interest looks at very high resolution. So this is the section of the small piece of the cortical bone from the vertebral body, and you see on the top control, and on the below is the diabetic bone. So we have more or less the same amount of vascular canals, and this osteocyte lacunae which reside the osteocyte cells are everywhere. But with time, we see that when they get old, the number of vascular canals which carry the blood vessels decrease in both, while the diabetic ones has visually much lesser vascular canals in the cortical bone. So it's not just cortical thinning and other parts. There's a lot of more things going on at the macro level. So we quantified those images in this one slide. So on the left, you see vascular canals. So initially, both diabetic and control rats had similar amount, but with time, this happens normally with aging. This is normal, but if you compare the 46-week-old rats, the diabetic ones had much lesser vascular canals. So their damage is kind of further deteriorated with disease. While in lacunar density, they also drop with the aging, the lacunae size. So the lacunae are getting shorter, maybe mineral infilling or by some other factors, but we don't see any difference with among the strains. So there are a lot more tests could be performed to answer like whether osteocytes are dying or not. But lacunae is the early indicator like what could happen. That's what I tried to say. And so all these mechanisms led to some kinds of changes in the mechanical properties. So we performed the compression test. We cut the top and bottom plates of the vertebral body and compressed them, and recorded how the stress strain curve changes. I'm going to present just main results here. So if we talk about elastic modulus, which is the ability of material to resist the loading. Because the bone is getting bigger, there's more cortical shells getting thicker. So the overall stiffness of the control vertebrae increases, while for the diabetic ones, it remained more or less the same. So it should have increased, but it didn't increase. While if we talk about the yield point is the point when the damage begins in the material during compression. So in terms of the load, we don't see any difference among the strains. But if we normalize these load values with the area, like we determine the actual material property, we found out that the control rates had declined yield strength, but diabetic has improved. So this sounds like, okay, this is good. diabetes is improving the yield strength of the material. But here's the spoiler. So this is the main takeaway, this slide, this picture. So with aging, control rats has an improvement in the failure load, like how much load you need to apply to fail the bone. But with the diabetic rats, it has decreased. So the bone is getting weaker, and you need to apply much lesser load to fail the material. But if you normalize this with the area of the bone, you don't see any difference. So it confirms that something is happening with the structure that is more a dominant factor in decreasing the mechanical properties of the vertebral bones. So to summary, in the seminar, I presented the number of ways that type 2 diabetes affects the vertebral bones with aging. And with growth, the growth is reduced. In terms of bone morphometric properties, the structure of the cortical and trabecular bone is also compromised, and mineral heterogeneity increases with time in the case of diabetes, and the cortical bone vascularization is significantly affected if you have diabetes. And lastly, all these things led to the reduction in the mechanical load to fail. So the main takeaway is that don't have diabetes. Thank you. So these are my supervisors and the funding, and the group members who were involved in somehow in this research project. Thank you.
Very much for that. That was impressive amount of work presented there. Really, really cool. Do we have any questions? Yes, Mom.
Because diabetes affects vascularity, is it likely that you've got a cause and effect? That the lack of vascularity or the poor circulation as the bone is growing is then resulting in stunted growth, and you have a causation that way? Or is that something you can't really see?
I think it could be an added factor, because there are more factors like is obese and other things are going on. But you're right, this could be an added factor, and because somehow vascularization affects the osteocytes, and osteocytes affect the function of osteoblast and osteoclast. So I agree with you. It could be an added factor.
You haven't
Yeah, we have not studied that thing. Yeah.
Another question, Sheila. Yes.
Mine actually follows on from that. So in addition to the vascularization, do you have any idea of the immune status and how the different immune phenotypes associated with type 2 diabetes?
What status?
Immunology of the disease?
Yeah,
How that's impacting the composition?
yeah. I think my previous group members who did the PhD on this study, they have a published thesis, and I'm not sure about they did a lot of testing on the serum blood markers and other things at a cellular level. So I have not correlated that. They saw some differences, but this study was I focused a lot on the X-ray based imaging, like what we get from this technique. So I'm not sure what happens with those. Yeah.
Can I just ask a follow-on? It's just a specific about the model. Is you've put them on a high fat diet? Is that high fat and high sugar, or just high fat?
I think it's high fat diet. I need to check how it affects the sugar, but I think we name it high fat diet. So I'm not sure.
Okay, thank you.
Any other questions? Rachel.
Have you checked that the way the bone is remodeling in the rat model is the same as what happens in the human diabetes?
Yeah, this is important, I think. Yeah. So recently, first of all, there's no study on the larger scale study on the vertebrae about the morphometric properties. There are a lot of studies of morphometric properties on long bones, mostly femurs, and particularly the trabecular thinning is observed in that. So the people who have diabetes have thin cortical bone as compared to their healthy counterparts.
So sorry, you mentioned at the start that the clinical bone mineral density, or sorry, the bone density scan is not different between humans. So why is it not different? How is it calculated?
They mostly use DXA or DEXA score.
Okay.
It's an aerial bone mineral density, but people have shown that whether you carry out this based on 3D or 2D, so that is I would say less accurate. Mm-hmm. And in this less accurate technique, they found no difference. And we did more accurate ones, and we also found no difference. So in validity, there is no difference between in mean mineral density. Yeah, so it's a very like the most complex thing with this disease, the bone disease, bones.
Any other questions from the audience? No.
Thank you.
I might actually ask you something. You know, you said the deterioration of those two types of bones were to different extents and different. What is your hypothesis behind that? Why do you think they were affected so differently?
I think the major factor is the vascularization and access to more other bone cells. So the trabecular, if I show you here, if you see the vascular canal volume is in the order of 3 to 4%, but in the trabecular bone is in the order of 0.05%. So that is also decreased, but that is already much lesser. So, and the trabecular bone has access to the bone marrow, so it has access to the cells, other cells. So
would that immune function then have a role more active in one versus the other? So that could be something.
Yes.
Okay. And also you use the Dragonfly software. How does the software work? What does it do? How do you analyze all these data? Sorry, big question here. It's curious.
It's a not too difficult software. If anyone has worked with ImageJ or standard image processing software,
it's similar.
Yeah, it's a more, I think, easy to handle.
Okay.
Maybe in 1 or 2 weeks, someone can master it, and then it depends on the applications.
Okay.
Yeah, but it's very handy to use those as compared to ImageJ.
And so if this is better, let me know.
It's surely better. If you are using like SBF-SAM or other FIP-SAM, and you want to highlight like mitochondria and these things in the cellular, it's very relatively easier to do in this software.
Very good. Great. Thank you. Well, thank you, Wahaaj. Thank you.
Thanks very much, Wahaaj. Really, really nice work. Our second speaker, is Federica Brescia. And Federica studied chemistry and pharmaceutical technology at the University of Naples Federico II, where she completed her master's thesis on the development of small organic molecules using flow chemistry for cancer immunotherapy. Currently, she's pursuing a PhD under the supervision of Dr. Luca Ronconi here at the University of Galway, and her project is focused on metal-based antiviral agents targeting SARS-CoV-2. So please welcome Federica.
Everyone, thank you for your introduction. I'm Federica, PhD student in Ronconi's group, and today I'm going to talk about my project. It is about the development of new glycoconjugates against SARS-CoV-2. So I'm sure you're all familiar with COVID-19, and unfortunately, let me remind you, it was the third time we had an outbreak due to the coronavirus family. So this data suggests that there might be a future one. And we still need large spectrum antiviral drugs. COVID-19 has already cost us almost $10 trillion. And just 1 month ago, there was the first historical pandemic agreement between the countries to invest even more money in the research and be ready for a future pandemic. Now, when it comes to develop new antiviral drugs, it's really challenging because viruses are really subtle. They hijack our cells, and it's very difficult to make a drug able to target just the virus and not the hosting cell. A promising strategy is to target one of these two proteases, one called papain-like protease, the other one 3C-like protease, because not only they are essential for the viral replication, they are also highly conserved in all the coronavirus family. So hopefully you can have large spectrum antiviral drugs. To the date, there are drugs approved against the 3CL Pro, but there are no drugs approved for the PL Pro. There was this candidate, but eventually never made it for the clinical trials. So my project focused on the PL Pro. That's the protease. It's a cysteine protease, And it's not only essential for the viral replication, it's also responsible to trigger our immune system. So if we inhibit this protein, hopefully we can also restore our immune response. Aranofin, that is a drug already on the market for other uses, has shown some promising results against the PLpro. The idea is that the gold can interact with this domain called zinc fingers. And what happens is that the gold displaces the zinc. And in this way, the protease loses its folding and cannot work anymore. I like to say that my project was born by a serendipitous discovery. That is a pretentious way to say by luck, because we actually synthesized these molecules as anti-cancer agents, but they were useless. And then it was an idea of our collaborator to test them against PLpro, and we got amazing results because not only they were able to inhibit almost 100% of the protease, they show an IC50 way lower of disulfiram. That is the standard drug reference for this assay. But when it comes to inhibit the full viral replication, so not just the enzyme, but the cell infected with the virus, these compounds were working, but at very high concentration. Even though at this concentration, they were still not toxic for health cells. So we wanted to improve these molecules, and we made a new rational design where we have a monosaccharide scaffold, so 3 different sugars to overall improve the solubility, decrease the toxicity, and see if they can target the glucose transporters. Then we have different linkers. The first one is based on the molecule I showed you before. Then we have here a triazole instead of an amide, because this is a bioisoster modification, so it's a different chemical group, but can give similar biological response. And then here we have an additional aromatic site, because in literature, usually molecules for PLpro have 2 aromatic sites. And finally, the constant part of all the molecule is a ditiocarbamate that has a protective chemoprotecting function, and the gold bromide that is the metal core. So mostly of my project was about the synthesis of these molecules, and the real challenge for me was to work with 3 different sugars, because even though they are similar, they actually show different chemistry behavior. To synthesize this first key intermediate, I had to use 2 different methods. One worked very well with glucose. The other one worked best with galactose and mannose. Once I got my key intermediate, I could proceed with the synthesis of the library. Here is a cupping reaction. Here is a click chemistry reaction, a very useful tool in synthesis. And here it's a combination of both. And again, I struggle with different sugars, while the first reaction with ethanol at room temperature worked very well with the glucose and kind of okay with galactose, didn't work at all with mannose. So then I had to push the condition using DMF, that is a very toxic solvent, and microwave at 90 degrees. So of course, then I got more side products because the conditions were harsher. Once I got my intermediate, before the gold, I generate these zinc intermediates, reacting in situ carbon disulfide and zinc. Finally, I was able to get my final compound with a transmetallation, and that's the libraries that I have synthesized with the 3 different sugars. A fair question might be, why transmetallation? Why we go through the zinc step? It's because we discovered that if you put gold straight away with carbon disulfide, you got a mixture of the desired product and a dimer, and these 2 are really difficult to separate. So it's worth it to add the zinc and have just the desired product without any further purification step. Since as I was telling you, I struggle a lot with some reactions, I decided to integrate the flow chemistry in my synthetic route. who is not familiar, flow chemistry, it's a different approach to do chemistry reaction. Instead of having a bottom flask where you mix things and you hope something happens, you have a continuous stream of solvent and reagent. They meet in a microreactor. So all the parameters are more under control, and in general, you get faster reaction or better quality. So coming back on the click chemistry I showed you before, there was a batch attempt with the MF. In flow, I was able to obtain the product in ethanol at room temperature. And it's not just a matter of having a greener solvent and no temperature, it's also a matter of quality. That's the NMR of the product obtained in batch. And that's after actually a purification. It's really not clear. There is something I cannot get rid of. But in flow, you can see without any purification, the product came out very clean. The only impurities is just a little bit of reagent because I use an excess of that. Once we finalized the synthesis of the molecules, I joined Professor Ingo Ott in Braunschweig to perform the biological evaluation. The first goal was to evaluate the infection inhibition. Now, if you want to work with SARS-CoV-2, you need a biosafety level 3 lab because there is the risk you can cause a pandemic, and usually colleges don't have this facility. So we decided to use human beta coronavirus as surrogate of SARS-CoV-2 because in this case, you only need a biosafety level 2. So that's an overview of the assay. You put the compounds with the cells and then you start the infection, you fix everything, and then you do an in-cell ELISA test. So basically you have an antibody that will link to the virus, and then the second antibody will link to the first antibody, and it needs to amplify the signal. So then you can see how many cells are still positive to the virus. And the cells we use are the rhabdomyosarcoma because they were suitable to host the virus. So before starting test the new compounds, we have to test again the compounds I showed you before because we want to see we are using a surrogate. Is that giving us the same results? And I know it's not very straightforward. In this graph, the red line gives us the IC50 of the inhibition because that's are the cells still positive to the virus, and we want to go to 0. But meanwhile, we also test the cytotoxicity, so the CC50, because we won't reach the 0 before the cytotoxicity increase. Otherwise means, yes, you are not seeing any more virus, but just because you killed all the cells. And again, we can see we reach the 0 around 500 micromolar. So that's the same results we got with SARS-CoV-2. So we validate that this system can be used as a surrogate. In this case, we also test a molecule without the sugar moiety. And with our surprise, it was actually the best candidate. That is almost 100-fold less than C50. And that was explained by uptake because actually the molecule without the sugar had the best uptake. But when we look at the inhibition of just the PL-Pro, the results were very similar between them. So it's probably just a matter of uptake. Finally, start the biological evaluation of the new compounds. And I left there the model compounds so we can compare the IC50. The first library is basically the same molecule. We just changed the sugar. And it was interesting to notice that actually different sugar gave a different biological answer. In this case, mannose was the best candidate, and it was 2 times more potent of the model compound. For the second library, the first 3 are the sugars with an acetyl group, and the other 3 are with free OH. In general, here we got better IC50 with the free sugar having a better IC50, with the only exception of the galactose protected that had a very low IC50, and there is a big difference between galactose and glucose. Finally, third library, that was actually our best results. We finally reached sub-micromolar IC50. And in this case, the difference between the sugar was not so big. So we chose galactose as the best candidate because he was less toxic overall. And that's an image of what happens during the test. The negative control, we just have cells without any virus. Then positive control is the virus that is full potential, is the green inside the cells. And then you can see how I increase the concentration of the compound. The green start disappearing, but the cells are still there. But when it comes to, again, test just the activity against PL-Pro, all the results were very similar between them. So the different activity might be explained again with uptake, but not fully, because that doesn't explain why different sugar has such a different activity. Since, as I was telling you, I synthesize also zinc compounds, so we thought why not test them as well, because in literature there are results of zinc compounds against SARS-CoV-2. And it was interesting to notice that the first two compounds without the sugar moiety were or inactive or extremely toxic, while the third compound showed an IC50 of 21, so it was actually stronger than the corresponding gold. But when we tested against the PL-Pro, we found out it was not active. That's a very high IC50 for an enzyme. So it works against SARS-CoV-2, but has a different mode of action. So to wrap it up, I designed 14 new molecules, optimizing the synthesis either in batch or in flow, and I did a preliminary biological evaluation. The ongoing is to evaluate the stability and solubility of these compounds and to perform cellular uptake studies, also with GLUT inhibitors, so to find out if they can actually target the GLUTs. I would like to thank, of course, my supervisor and all the collaborators to this project, the funding, and you for your attention.
Very much, Federica. Very, very impressive work. Does the audience have any questions for Federica? Sheila?
It's interesting the difference you're seeing with the different sugar moieties and sugar versus zinc and so on. Do you have, and this might be crazy, but do you have any idea as to whether the different sugar and zinc attachments are impacting the metabolic activity of the cell and therefore indirectly having a positive or negative effect on viral infection?
That's a very good question. I don't have any proof right now. The first thing will be for sure to see if they have different uptake, so if the sugar is affecting the uptake. I honestly don't think they are affecting the uptake because overall they are very similar in terms of solubility. I think what can happen is since usually mannose and galactose give me better results than glucose. The difference is that both of them have an axial OH. So maybe this OH is able to do a hydrogen bond that the glucose cannot do. I don't know if this is the case while it's entering in the cells or while it's interacting with the protease. But so far, I think it might be the only explanation.
I'm interested to know, why did you choose CACO, is it, cells to test these compounds? And a follow-up question, do you plan to do any in vivo work on these compounds in the future?
Maybe. The CACO cells were used with the lead compounds for the toxicity, and I think at the time we were in lockdown, so it was more a matter of what we have already in the fridge because everything was closed. But then when I did this test now, we didn't use CACO cells, so we use RD, rhabdomyosarcoma cells, because they are suitable to cause the virus, but it's more a matter of the difficult thing about this test is the productivity of these results, because all the process is very dynamic. And before you start, you have to do a titration of the virus. So you have to stabilize to say how much virus you have in your medium. And these cells are good to do a test that is called the plaque assay, that needs itself to do the titration of the virus. So that's the real reason why we use RD cells. For in vivo studies, I think we are a little bit too far away. These compounds are good, but I believe we can still improve them before give it to the rats.
Maybe sometime in the future.
Maybe sometimes.
Federica, very cool work. You know, you've done a flow reaction and you saw better results. Is it similar quantities you're using in your batch versus flow, or is there any advantage of the flow with the microchamber that there's like maybe a solid phase support there or not, or what are the differences? Can you tell me a little bit more about that?
In flow, I actually use less concentration of the reagents, but the flow reaction only lasts 5 minutes. So even if it's less, you can just keep going. The biggest difference, as I said, was the quality beside the solvent and the temperature. I'm trying to improve the overall process with the solid resin. For example, a resin that can catch that reagent in excess that I was showing you before. And also I would like to translate the azide reaction in flow, because when you do azide, you use sodium azide, that's dangerous. And in flow overall should be safer to do that. And you can use a resin to give azide, sodium azide.
How do you then purify the copper out of your reaction when you've made your products? How do you get rid of the copper?
Since my sugar are all protected, they are not soluble in water. I do an extraction of water organic phase. And if you really want to be sure to get rid of the copper, you can use IHDI in your water phase, because it catches the copper.
Thank you.
Any other questions from the audience? May I ask one last question? The stain that you use, light microscopy. So what's that stain you use to track the virus? The DAPI, I know, with the green.
It was a specific antibody for the virus that then stains green fluorescence. If I have to remember the name, honestly, I don't.
Very nice.
It was some rabbit antibody.
Very nice pictures. Okay, well, thank you very much for a lovely talk.